Hi, everyone. Welcome to this invited session called Spatio-temporal Modeling of Environmental and Climate Data. So this is sponsored by the RSS Environmental Statistics section, which I'm involved in, and Pete has been involved in a lot as well, one of our speakers. I think I'm allowed a shameless plug if it's for RSS. So in the chat, you will see a link to the Environmental Statistics webpage where you can join the mailing list and find out about all our events. We have many sessions at this conference, but we also have events in between, and we're really trying to ramp up our activity, especially with COP26 coming up in Glasgow, actually, later this year. We've got a series of meetings planned next year, which are related to discussion papers on statistical aspects of climate change. It's too late to submit an abstract for that now for a paper, but when the papers come out, they're discussion papers. So we invite all of you to, if you have something to say about any of those papers, to publish your discussion contribution, which would go along with the paper in one of the journals of the Royal Statistical Society. So there's a whole bunch of exciting meetings coming up later this year and next year. So with regards to this meeting, we've got three speakers whose their videos are on now. So I encourage them to give a wave so you know who we've got. We've got Marian, Phil, and Pete in that order. They're going to have 25 minutes each, including questions. The way we're going to do questions is to take them at the end, because that is a bit easier with the online format, just to keep the flow. But you can type your questions in the chat where you see I put that link during the talk. And what I'll do is, you'll have that preference in the running order for questions at the end. So do type those in case we run out of time to get your question in. There's also a raise hand feature. So towards the end of the talk, raise your hand if you have a question. If you do it at the beginning, I'll wait to the end, just like I said, in the interest of time. But please do ask questions. Speakers will try budget time for that. I think that's all the announcements I had. So without further ado, let's get going. Our first speaker is Professor Marian Scott from University of Glasgow, Department of Maths and Stats, who's broad expertise across statistics and environmental sciences. So we're absolutely delighted to have you here for this first invited talk. And over to you, Marian, and I think you're going to share screen for your slides.
Yep, thank you. So thank you very much, Adam, and thank you very much for the invitation. I hope technologically this will all work very smoothly. So what I'm going to do today is present an overview of a project that I've been involved in. It's a digital environment project, and I'll give you a little bit of background about where the funding for this particular project came from. Now, this particular project, as I said, it was described as a digital environment project funded by UKRI NERC, so the Natural Environment Research Council. But the particular project that we were involved in is called Understanding Water Resource Usage Using Sensors and Satellites. And the pictures on the left of the screen basically show some of the installations that we undertook in the particular catchment where our project was based. So that's if you like, the kind of background to a little bit of what we're going to talk about. So as I said, the funding was provided by UKRI. It had a terrible title for a project, a digital environment for water resources, but I'll explain what we were meaning in that context. And we had two additional partners, the Scottish Environment Protection Agency, or SEPA, and Census, which is a Scottish Funding Council-funded innovation centre for sensing and imaging. And Census actually built some of the sensors that were deployed in our catchment. At Glasgow, the people involved in the project were myself, Claire Miller and Sir Rajat Ray, and then two postdocs, Diana Georgitou and Craig Anderson. So I was going to give you a little bit of background about the Digital Environment Project. This was a strategic priority funded area within EPSRC and NERC. And it involved a number of different objectives, in particular, the use of integrated or networks of real-time and near real-time sensors across the natural environment. And so there was an element of building kit, communicating data coming from those pieces of kit that have been built, thinking about the infrastructure that was needed in terms of storage and access to these different data streams, and then manipulating and managing the different data streams that had been produced, modeling and visualizing, as it says, at a high resolution in terms of spatial and temporal scale. So this was I think a 2 or 3 year program. It's at an end currently in the sense of there's no further funding calls, but the hope is that the research councils will continue to fund this particular area. As I said, £10 million committed. There are 2 champions of this whole area within NERC, and I'll mention them later. There were 17 projects funded, etc., etc. And there's been a whole host of different ranges of types of activity, not just simply the funded projects. And there are dedicated web pages for the programme, and hopefully you'll see the links to those either at the bottom of this particular slide or at the end. So the project that I was fortunate enough to be awarded was to instrument a rural catchment in Scotland with new small sensors specifically for river level and soil moisture to provide near real-time information on water quantity in really quite a small river network to various stakeholders, but predominantly farmers. The catchment that we're referring to, you can see in the map of Scotland. It is a very small catchment. It's not large in that sense. It's called Elliott Water. And the picture at the top just kind of zooms in on that area, shows you the extent of the catchment and shows you the river network within the catchment and where some of the sensors have actually been positioned. Now, there were lots of challenges. So this particular project, it was a 2-year project. The intention was never to get to fully sophisticated statistical modelling of the data, although if we did, that was a bonus, but actually just to tackle some of the basic challenges in thinking about laying out networks of sensors, thinking about the data quality assurance, and then thinking about how we use the data coming from the sensors to actually improve our intelligence about water use. As I said, this is a rural catchment, so water is extracted at times for irrigation. And SEPA regulate water extraction within Scotland, but only really at a very aggregated level in terms of a yearly figure. So when you think about maybe multiple farmers trying to extract water from the same river system, it's actually much more useful to know something about when they're extracting at a finer resolution and certainly an annual level. And as I said, many of the sensors that we used were actually newly designed and built in collaboration between SEPA and Census. So there certainly were some interesting challenges around data quality assurance, which I'll show you later on. Now, where did we get involved initially? Well, obviously, one of the initial things is to think about where are you going to put the sensors. So we actually did a statistical design using a GRTS framework, which was developed by the US Environment Protection Agency. We knew how many sensors we could afford. And so we basically came up with an optimal sampling strategy using that number of sensors. Of course, we then had various conversations, in particular with SEPA, who installed the sensors, because they had to liaise with the farmers, we had to understand about ease of access, we had to understand about security of where we were installing the equipment. So if you like, the theoretical statistical design was also moderated to take into account some of the practical, considerations. Now, communication is a really interesting problem in the sense of these sensors were streaming data live, but you have to be sure and confident in terms of the ability to communicate. And while the catchment is rural, It's not so very far away from a reasonably sized town in Scotland, but we still had a number of, if you like, black holes within the catchment in terms of communication. So we also had to think about how to improve the actual coverage within the catchment, whether it was to do with the topography of the area and so on. So there were a number of bits of work done in terms of thinking about where to install specific communication facilitating kit to ensure that we could actually communicate from across the whole catchment. We did also use, for a small period of time, just to trial a local satellite operator to effectively use that as a means of communicating the data from the sensors to the cloud and then obviously to extract it. But that was commercially quite expensive and not something that, in a sense, we wanted to use and be the only solution that we had to these holes in terms of the gaps in coverage. Once we had solved those problems, then the whole idea was that the data could be extracted live and it could be extracted for each sensor. And then those live data streams could be created and looked at either by the farmers or by SEPA or by whoever was interested in looking at the data. And these would give instant access for the users. So that, again, certainly not my particular area of expertise. And that was really, again, where the census team, particularly working closely with SEPA, facilitated the data being streamed for us to use. So what did we have? We had our sensor data. So these are the in situ sensor data, typically 15-minute resolution. We were measuring things like river level, humidity, and soil moisture. We have across the catchment 4 different types of sensors, again, just to allow us to effectively evaluate which ones were the most robust and so on in terms of streaming data reliably. There are currently in operation something like 20 plus sensors, and we have an additional 10 still waiting to be deployed. We had a very significant gap in the middle of the project as we all went into lockdown. SEPA staff were no longer doing field work, so we had quite a long delay in terms of having the sensors built and then having them installed. So the length of data record we have from our sensors is still quite short. We only really have something just over a year's worth of data. At the same time, we've been making use of some of the national monitoring network data from the Cosmos network. There are multiple sites in Scotland, and they're not specifically exactly in our catchment, but some of them are quite close. And the one in Bulrudry is the one which is closest. Now, these are particularly focusing on soil moisture. They're 1 hour resolution, and we have data effectively, as I said, we started in 2015 to pull those data from the Cosmos network, but all the way through to currently. So as I said, our sensor data have been operating for about a year. We've got the Cosmos data. We've also got Met Station data, since soil moisture clearly must be related to how much rain there has been. We broadened our remit to look at some satellite data as well. So we've also been extracting Copernicus land monitoring data. This is a 1 kilometre resolution, which is quite large for such a small catchment, and I'll show you some pictures in a minute or two. And we also acquired 4 overpasses from the Japanese Space Agency of ALOS-2 satellites. Now, these are 10-metre spatial resolution, and it's radar imagery, so much finer spatial resolution, but also much more complex to deal with from the point of view of the pre-processing. I mentioned that one of our kind of tasks was data quality assurance, because without a doubt, we sometimes underestimate just how much work is needed in preparing the data before we do any modelling. So there are a variety of technical issues that can often occur in sensors which are installed in remote locations. We wanted a situation where the SEPA guys didn't always have to be dashing out to the field, because it's quite a long way from their particular office, to repair faults and so on. So the types of issues we're talking about low battery, sensor drift, calibration fault, sometimes just going offline, and so on. And so what we've done is we basically looked around, and we came across some very interesting work that was undertaken in Australia, looking at exactly these types of issues, an anomaly detection framework. And so we've implemented those ideas in our system. And there's a whole variety of different types of anomalies. I'm using that word very generally, but it could just be simply impossible values, or drift in the sensor, or changes in the variability. I mean, missing values, I guess you wouldn't necessarily describe as an anomaly, but it's certainly an important feature that we had to think about. And again, we wanted some form of automatic flagging system that might simply say to, again, the guys in SEPA, for instance, who are looking at the data and using the data, there's maybe something slightly strange happening here, and then they can explore it further. So we weren't proposing automatic solutions, but simply automatic flagging, so that they could be looked at as the flag popped up. Now, these are just a couple of examples, a few of the sensors here. These are from sensors, the model called Hygro. The plot on the left is the hourly air humidity data. The plot on the right is air temperature. And you can begin to see some of the issues in some respects that we encountered. And as I said, these sensors are new, they're being built, and they're being tested. And a number of issues, design issues, are kind of, I think, apparent and are being remedied. So, for instance, with respect to humidity, the sensors are placed in a metal box typically, and then installed in the catchment. And what we discovered in some respects is that there's an issue because, if you like, moisture builds up within the box, the sensor gets saturated, and so we end up with these, if you like, values, as you can see in the plot on the left, hitting 100% and then not changing. Temperature, like many environmental variables, is very well behaved, and we had no particular issue with our temperature sensors, but the humidity sensors are definitely ones where there are some design features which are currently being improved. We still wanted to try and model them because it's not a problem that occurred with all of the sensors. And so we've been building, if you like, basic time series models with long memory effects in this particular situation to try and allow us to build a model that describes the features that we're observing, partly because, as you'll see later on, we also wanted to develop a use case, which is to produce something which is called the Hutton criteria. So we needed to be able to make forecasts of humidity and temperature to feed into this use case, which we hoped would be useful for the farmers. In terms of the comparison between our own sensor data and Cosmos, you can see here again our own individual sensors, the Hygro with the Cosmos UK identified in the large cloud of points. You can see there's a similarity in terms of trends and perhaps some features, but they're not exactly identical. Now, part of that is clearly the Cosmos system is not in the catchment, and soil moisture is likely to be something which is pretty localized, because you can immediately see the differences between the different sensors already in the catchment. But again, the Cosmos network is very well maintained, very well calibrated, its features well understood. So we wanted to have that opportunity to look at the relationship with our local sensors and this national data set. Now, I mentioned the use case. I'm not going to show you the Hutton criteria, but it allows you to evaluate the risk of blight infection in potato crops. So commercially, it's really very important if you're a potato farmer. As I said, it involves temperature and humidity, and there are specific rules about when the criteria is, if you like, flagged. It's used by farmers to provide warning indicators of up to 24 hours in advance, which they can then, if you like, take remedial action to avoid the issue. So we've been developing with the sensor data that we have some localized, if you like, calculations of the Hutton criteria, which we can then feed back to specific farmers for their specific fields as well. The soil moisture calibration we're continuing to work on. It feeds really well into the drought management system which SEPA operate. And surprisingly, as it may seem for those of you that know Scotland, it's not often thought as suffering from drought, but in actual fact, for several months of this year, our catchment that we've been studying has been very, very dry. So here we're dealing with a situation where we're trying to calibrate our in situ sensor data with the Copernicus open source data and a few high resolution satellite images, because the high resolution satellite images we have to effectively pay for. And we've been developing with a colleague, Craig Wilkie, who published a paper, it says 2017, that's a mistake, it's 2019, what we've called non-parametric statistical downscaling to allow us to build a joint model for the satellite images data and the sensor data to improve a joint visualization of what's actually happening in the catchment. And I just got a couple of pictures here. Now, the two plots on the left are from Copernicus, 4 days apart. You can see quite clearly the pixelation in terms of the 1 kilometre spatial resolution. The two pictures on the right are of 1 day and they're 10 metre resolution. And because this is radar imagery, we actually have two measures, anisotropy and entropy. And we need to think about how we bring those together as a single measure of soil moisture. So that gives you a measure of, as I've said, the differences that we're seeing between the different satellite imagery. And the ALOS 4 images we have span dry and wet periods. So some of the statistical challenges that we've encountered, just really the quality of the data from these newly designed sensors, the varying levels of uncertainty, the variation in the spatial temporal scales. COVID is going to affect everybody. And just thinking about statistical methods to bring together all of these different data sources so that we can feed that information through into things like the Hutton criteria for use by local farmers. So the digital environment, I think, whole concept is that we have a wealth of data, lots of new instruments being put out, generating lots of extra data that we can look at with different spatial and temporal resolutions, different levels of accuracy, requirement for really serious quality assurance. I'm thinking about these novel statistical methods that allow us to combine these different data sources to produce maps and uncertainty that can be fed through to the end users. And just a couple of references there and an acknowledgement for the use of the Cosmos data, which is owned by the UK Centre for Ecology and Hydrology. And that was pretty much all that I had to say, Adam. I can stop sharing if that would be useful, I hope. And I'd be very happy to take any questions if anyone had anything. I think I'm on time, I hope.
You are more than on time. We have time for questions. Thank you so much. I see some people have already found the reactions tab to give a round of applause or other reactions. So please join me in doing that to thank Marian for her talk. Thank you, everyone. Can you see that, Marian? Lots of
yes, thank you.
Hands clapping. And imagine a sound in your brain for that happening. So also in that reactions tab, now that you found it, there's this raise hand feature. So if you did have a question, either start typing it in the chat or raise your hand and I'll cue you in. That might be the most sort of orderly way of doing it. And while that's happening, I thought, a comment that it's really interesting how, especially for spatio-temporal, like you can't ignore all the things that can go wrong in measurements, right? And I think I'm probably grateful for receiving relatively clean data because someone's done that work for me. I thought it was interesting that you mentioned for the humidity data that you said that there was this element of long memory.
Mm-hmm.
And is that, does that, I guess my question was, like, you said that you could still work with the data even though that there were these bias issues is that because of this aspect of long memory that there's enough dependence in the data that you can kind of forecast forwards before it breaks down, like the dependence helps you?
Yes, I would say that's very true. And I think the other thing is, as I said, it's a relatively small catchment. And what we've been trying to do is trying to kind of borrow some information from the sensors that are closest to if we're looking at a sensor by sensor discussion in terms of forecasting, we're using information from the sensors around it as well. But the in this particular case, the long memory, I think, does help us. We're not trying to forecast a long way ahead in that sense. As I said, the farmer.
Resort actually have a battle companies campaign, like battle report.
And we've got someone came unmuted there.
Yeah, that guy, the when they did the Weathertop battle report.
Okay,
yeah.
I think we're
so just from that point of view, it does help. I mean, as I said, we're talking about probably something like 24 hours maximum, and just to give the farmer enough heads up, for instance, that they might want to think about extracting and irrigating, that type of thing, or taking any other remedial measures that they have. In some senses, the project hasn't delivered everything that we'd hoped, because in a way we wanted to have more sensors in the catchment than we currently have. We wanted to have a longer length of time so that we were covering 2 growing seasons, if you like. And in actual fact, because of as I said, just the whole COVID situation, everything got delayed. So we've kind of had to work with a less ideal situation than we had originally planned from that point of view. And I think our ability to get out into the field as well has been compromised by COVID, just simply because of lockdowns. So in that sense, we've done the best that we can in these circumstances where, as I said, some of the design issues with the sensors, I think if we'd been in the field earlier, we'd have caught quicker, so we could have improved some of the quality of the data that we've also been receiving. But in general, as I said, as a proof of concept, which is what it was originally intended as, it has demonstrated that it is possible to deliver this improved product at a temporal and spatial resolution that is useful to the user community in that regard.
Yeah, there's actually a nice follow-on question in the chat from Meave, who says, really nice talk. How will the humidity measurements be corrected? What will the metal box need to avoid this in the future?
Yeah, so, well, there's two approaches. The physical answer is that the box has been redesigned so that the sensors are now placed in a box where there's much more, if you like, exchange. And so the humidity build-up within the box has not 100% been resolved, but it certainly has been considerably improved. In terms of the data that we actually have, from the point of view of what are we going to do, in the sense of I'm not prepared to say I can't use any of it. So in part, that's why we've gone to look at other networks. So accessing, as I said, the Cosmos data, it's not precisely in the catchment, but at least if we can begin to get an idea of what the kind of larger scale changes might be. We're also looking into the kind of more local meteorological information to see if we can begin to develop a model, I suppose that you would say, will make some adjustments to allow us to still make use of the data that we actually have. And as I said, it's not a feature that has manifest in every sensor, which is part of the challenge in some senses in that regard. But from a project point of view, I think it's been a really interesting learning process for us, just again to kind of, I suppose, emphasize the challenges that there are often in the technology that we want to use and the data that the technology are generating. But from the SEPA point of view, the sensors, the project has now finished, but the sensors will be maintained. The data is continuing to be streamed, so it's continuing to be used. And I think, across the three organizations of the university, Census and SEPA, I think the collaboration has really been very productive from the point of view of both from the design of where you put your monitoring networks, the technology of what it is you're able to measure, and then, if you like, the kind of analytics of how do you handle the data coming in, dealing with some of the anomalies that we've identified, thinking about how we can use that to make forecasts going forward at these spatial scales that are meaningful for individual farmers in terms of field sizes and so on.
Terrific. That's very interesting. Very interesting. Well, thank you so much, Marian. We don't have more time for questions. In the interest of time, we need to now move on. But thank you again. And next we have Professor Phil Jonathan, who is a statistician at Shell as well as a professor at Lancaster University. I won't take up any more of your time, Phil. Over to you.
Okay. Hi. Thank you, Adam. Well, thanks everybody for turning up to the talk for the first place, and thank you for the opportunity to speak. So this talk is about multivariate spatial conditional extremes. So it's joint work with Rob and Emma, who are statisticians who both did their PhDs at Lancaster, and with Augustinus and Ian, and they, I guess, are wave specialists, so you might count them as kind of ocean engineers. But in particular, in recent years, they've been working on the satellite data and observing the ocean environment using satellite, right? Okay. I'm going to be skipping a few slides. So the full slide pack and the draft paper actually on this stuff is available at my Lancaster website. Okay, so just an acknowledgement to John Thorne and to Jenny Wadsworth at Lancaster and to my colleague David Randall at Shell. So really the motivation behind all of this work is how useful are satellite observations for the ocean environment? So again, we're thinking about maybe designing structures, locating wind farms, etc., maybe coastal defenses, right? So from that kind of engineering perspective, right? And when is it likely that satellite or direct satellite observation might become primary data sources for decision making? And given that a lot of that decision making from design has to do with extremes, so extreme environments, we're interested about the characteristics of extremes coming from satellites. And here in particular, what we're going to be looking at is spatial characteristics. So we want to know about extremes occurring at the number of points in space at the same time. But also we're going to be looking at multivariate spatial extremes. So we're going to be looking at the extremes from a number of different quantities or a number of different spatial fields, if you prefer to say it like that. So this work is really the latest in a sequence of publications in this kind of area, and it all is underpinned by the model of Heffernan et al. 2004. So anybody who's familiar with that will basically get the rest of the talk quite easily. But I'll spend a little bit of time explaining what that model is, and then there are various extensions to spatial conditional extremes, applications to satellites and to hindcast data, and now the current work, which is a multivariate extension, a multivariate spatial extension. So I guess if you're thinking about competitors to this approach, then it would be people in the extremes literature who work with MSP, so max stable processes, and then there are various extensions of those like hierarchical max stable processes and then multivariate max stable processes. And Reich and Shabi, Genton, Husserl, Wadsworth and Vittori are kind of notable in that area. So yeah, so what am I going to do? I'm going to show you some satellite data and some hindcast data. I'm going to give you a very, very brief overview of the methodology and then show some results for the North East Atlantic between the British Isles and Iceland. and then some a summary at the end with some practical implications. Okay, so this is the important slide, right? So get this, and then we're cruising, right? So imagine that we've got a set of points between the British Isles and Iceland. And imagine at each one of these points, we're going to be observing a lot of different quantities. So what we're going to do is we're going to assume that one of those quantities, the green quantity here, right, is going to have an extreme event at the square, right, at the southwestern location on this transect. So what we're interested in knowing is what is the shape, what is the profile, what is the joint spatial distribution of all of the quantities at all of the other locations, given that you have an extreme event of that one green quantity at that location. Okay, so we are in a condition on a large value at the conditioning location. The quantity is going to be called x01, so it's at location 0, and it's the first quantity. And what we want to do is to estimate things like conditional spatial profiles or this joint multivariate spatial structure. And the way that we do that is actually relatively straightforward, at least in principle. It's a kind of a copular model. So what we have to do is a dependence model, if you like. So what we have to do is, first of all, transform the data from all locations for all quantities onto some sort of standard scale. And in this case, we're going to do that transferring onto standard Laplace scale. We have to, so that involves some marginal or extreme value modeling, and I'll explain that a little bit. Then we have to set a really high threshold for the conditional location. And then we adopt, which is essentially the conditional extremes model. So this is the basic result from Hefner and Thorne in 2004, which says that the joint structure of all of the other variables here at the remote locations, given an extreme value of the conditioning variate, takes a particularly simple form. Okay, so it's kind of like a regression relationship, you can think of it, right? So alpha here is going to be a vector of kind of slope parameters, one for each one of the x's, and beta is going to be like a vector of kind of scale parameters, if you like. So then Z is a spatial, a multivariate spatial residual process, or a distribution if you have a finite the set of points here, and we're going to describe that based on just learning from past experience. We found that a delta Laplace model or a generalized Gaussian distribution is a good way of describing that residual process. So really what we're about then, and then this residual process has got all of these parameters in it. Essentially, some of these parameters vary spatially smoothly because they're telling us about the decay or the evolution of the parameter in space. And sigma is kind of like a correlation for this process or distribution, and it's actually it's a correlation matrix for a conditional Gaussian field, and where the decay between points is kind of a powered exponential kind of deal. Okay, so that's essentially the methodology in a nutshell. Now that I've told you that, the rest of the talk is basically just taking you through some pictures, right, to show you how different things work, right? So satellite observations, there's basically altimeters, radiometers, scatterometers. Altimetry is definitely the best way of measuring HS. So that's significant wave height. So that's the roughness of the ocean surface, so that when people are talking about storms, they talk about HS, they talk about significant wave height. Scatterometry in general is the best source of wind field data, so that's wind speed, 10 meters here, and the direction. So overall, you can see from the schematic on the left-hand side, we've got around 30 years worth of data if we're lucky, right? But the spatial coverage is by no means complete. So you're typically getting one observation per day from each satellite, right? These polar orbit satellites and stuff. And also for things like HS and U10, calibration of the satellite output is also necessary to buoys or to reanalysis data sets. And again, this is where Augustinus and Ian are kind of experts. So we're going to concentrate on one particular set of satellites. So these are the METOP satellites. As you can see here, they're scatterometers, and you can see from this one that METOP C has only just been launched in the past couple of years. Okay, we're also going to look at hindcast data. So what's a hindcast? Well, hindcast is a physical simulator of the ocean environment. And again, it's calibrated to do observations, typically buoys. And we're going to look at one hindcast in particular, which is NORA 10, and this covers the North Atlantic or the Northeast Atlantic. And data is available for a much longer period for these hindcasts, right? So the original objective of the work was to try to use altimetry, JSON, the satellites, to use scatterometry, METOP, and NORA 10 together to build this multivariate spatial extremes model. But unfortunately, joint occurrences of JSON and METOP are really, really sparse. They're really rare. So it became very clear at the beginning that this was not going to happen. So what I'm going to talk about here is just an analysis built on METOP and hindcast data. Okay, I'm going to skip that slide in the interest of time. So these are just swaths from the satellite. The satellite comes from the northwest to the southeast. This is Iceland here. Imagine the UK here, right? All I want to tell, and the coloration is indicating wind speed. Red is high, blue is low. So clearly, right, the scatterometer is picking up obvious profiles of the wind fields corresponding to storms. And this is the kind of stuff that we're expecting to be able to pick up in our models as well. So to make life simple, we take these registration locations, as I've already illustrated that to you. There are going to be 14 of these. And again, what we do is essentially we take the closest, the near neighbors, if you like, from the satellite swaths, and then near neighbors in terms of space and time from the hindcast in order to get this kind of registered set of data on these 14 points. But just to emphasize, we have satellite wind in green, we have hindcast wind in orange, and we have hindcast wave or significant wave height in blue, right? So we're going to be interested in the joint structure of all of those quantities across space, but conditioning only on the satellite wind speed, the green variable at the conditioning location. Okay, so this is just some motivation about the data, right? All of these plots have the satellite wind speed at the conditioning location on the x-axis. So what we're doing on the y-axis is looking as a function of distance around here, but then you're looking at the three variables in these different columns, right? So unsurprisingly, I'm looking at like with like at zero distance. As distance increases, then the dependence between satellite wind at the distant location and that at the reference location decreases. And you might say that after maybe, let's say 1,000 kilometers, it's effectively zero. It's effectively like it looks uncorrelated, right? The same kinds of story for the hindcast wind speed. You'd expect it. They're trying to measure the same physical quantity. But then hindcast wave gives us this kind of curvature. And again, this is kind of typical. This is the drag or U, if you like, right? So it's kind of the wind blows over the water, and it's kind of a wind speed squared kind of effect in terms of energy transfer to the significant wave height. Unfortunately, we have covariate dependence in all of these variables as well, right? So we have directional variability of the quantities, and we also have seasonal variability of the quantities. So the last three columns shows the season variability, and you can see that this is kind of standard across the three quantities and across space going down the columns, down the rows, I mean. And then on the left-hand side, we have the directional variability. Now you can see that this is kind of, you can see the westerlies here, right? 270 degrees, right? So these are westerlies which are prominent in significant wave height. They tend to be there maybe at these locations for the hindcast and for the satellite wind speeds. But you can see that the characteristics are changing as we move essentially between the UK and Iceland, right? So we need to be careful and map those characteristics faithfully, if you like, when we're going to standard Laplace scale. So again, I don't want to label this slide either. So what we're going to do is we're going to fit a non-stationary directional season extreme value model. And the whole purpose of this model is just to map the data set that we have from the original physical scale to a standard Laplace marginal scale. Now, when we're doing this, I want to flag some deficiencies. We're not propagating uncertainty from the marginal fits through to the Laplace scale, okay? And we're doing those fits at the moment independently per variable, per location. So clearly there are some improvements we could do there. But on the Laplace scale, this is the corresponding data that we would see. Again, you've got satellite wind speed at the at the conditioning location on the x-axis, and now you can see these plots are actually direct evidence for what you'd expect to see in the conditional extremes model. Imagine conditioning on a large value of the x variable here. You want to know what the slope of the y is, essentially, right? So when the distances are small, then the slope is going to be near unity, okay? But when I move to much larger distances and I condition on a large value of x, then the slope is going to be near 0. Okay, so this is this alpha term in the conditional extremes model. So I can see that alpha term is going to decay from around unity to 0 over this distance. And the same kind of thing, same kinds of characteristics you can see from the other slides as well. Okay, so a little bit on the conditional extremes model. So this is what Heffernan and Thorne found, is that for a large class of bivariate distributions, you can write the conditional distribution of a variable y given a large value of another variable x in this form, where z is some unknown residual, but the residual is kind of estimated or characterized empirically. So for example, for fitting, we might take a normal, okay? So then essentially model fitting means fitting alpha, beta, mu, and sigma, okay? You can look at what the conditional mean and the conditional variance under that model assumption is, and these are the forms that you get. And you might suspect that there's going to be some identifiability problems. For example, when beta is around 1, it's going to be pretty hard to identify alpha from mu. And you see some of those effects generally when you're fitting these kinds of models. So the extension to spatial conditional extremes, the model form looks the same, right? But all we're doing now is, instead of looking at one variable here, one conditioned variable, we're going to look for Q conditioned variables, and these Q points are points in space, so they're going to have some spatial characteristics as well. And this is where the form then of this residual distribution or residual process Z becomes important, and why we've chosen this delta Laplace. Okay, so there are various reasons why we've chosen the delta Laplace and why we've chosen the power exponential decay with distance for the correlation matrix psi. And again, that's explained a bit more in the paper. Model fitting means basically estimating these distance parameters and also estimating the correlation parameters. So that's spatial conditional extremes. Now we go to multivariate spatial extremes. Again, model formulation looks very similar, except what I have now is that I'm now going to have a condition set for m different quantities at q different locations. So really, in terms of the marginal effects, the model looks the same. All of the detail is in this residual again, right? Again, it's a delta Laplace, but now the correlation matrix has to take into account the decay with distance, let's say for a particular quantity, but also the cross decay between the various quantities in the model. Again, model fitting, I've got some extra parameters in here because of the cross decay, but model fitting is basically the same as for spatial conditional extremes. So
5 minutes, Phil.
Yeah, good. So we use MCMC with piecewise linear forms for the parameters. For the case we're doing here, there's like 150 parameters, and the convergence is really good. So 10K iterations is typically okay. So just to finish, we'll just show a couple of results from the method. So this is the decay of the alpha parameter for the 3 quantities, satellite wind, hindcast wind, and then the in order, right? And then hindcast wave. So this is showing the typical ordering we would expect, right? The other parameters are coming out much of a muchness. And again, these parameters have limits and have bounds and things, and those bounds are being satisfied here. So that's kind of promising. Then what we can do is we can look at conditional mean profiles, if you like, for very large values at the conditioning location. And again, we're getting the same kinds of characteristics out as we would expect. Interesting here, right, is that the spatial scale for the decay of this extremal dependence looks to be about between 600 and 800 kilometers in the Northeast Atlantic, which is kind of like an interesting figure for the physicists. Again, these are just showing that we're getting a good model fit. Essentially, these are just various diagnostics looking at marginal and residual samples. So yeah, so this is the last slide. So in terms of data, we couldn't use JSON and METOP together, unfortunately. We can get by now about 2,000 good daily observations for the METOP satellites. There's a bit of sampling bias because the swaths pass over the North Atlantic at the same time each day. And the data are kind of instantaneous, not storm peak. And typically the engineers like to work on the worst thing that's going to happen in a storm, not an instantaneous value of the quantity. Methodology is fine. The structure that we've assumed, especially for the residual process, seems to work really well and fits pretty well. And then physically, in terms of the results, I think the most interesting thing is the spatial extent of 600 to 800 kilometers for the extremal decay. Thank you, Adam. That's it.
Great. I didn't mean to rush you there.
Oh, that's all right, man. That's fine, man. It gives a chance for a few questions, right?
Exactly. So that's, again, if we go into the reactions, we can give Phil a clap or a different emotion for doing that. Give a thumbs up as well. Yeah. So yeah, thank you very much. Yeah, see lots of rounds of applause there. Oh, we got a party celebration there coming through. That's a nice.
We've even got some comments in Welsh, man. Highly approved.
Oh, okay.
Thank you, Michael. Thank you, Michael.
Get my Google Translate out. But, great. So the other reaction there, which I encourage you, is a raised hands, and I see we have one already. Others can join the queue. Please do. We've got 3-4 minutes for questions. So I'll go to Daniela first.
Hi, Philip. Thank you very much for a very nice talk. So I have 3 different questions. I'm going to start with a very natural one, which is, how do you choose the site you're conditioning upon?
Okay. Yeah. Okay. Well, again, that I think to be honest, that's quite arbitrary, right? The work we were doing here was just to develop the method, so there wasn't a particular interest in one site, right? But say from an engineering perspective, maybe what happens is, right, where a particular asset, let's say like a wind field or like an oil rig or some submarine asset is going to be located, or it could be like, a coastal wall or something, right? And then what you're interested in is mainly what's happening around that asset, right? So you have a particular focus on one location, and what you're interested in is to know what's actually happening, let's say, relative to that asset, right? That's one of the deficiencies of this kind of approach, to be honest, right? The max stable process models, they have lots of other problems associated with them, but what they do, which is better than this approach, is that they do try to model the whole spatial field, not just conditional on large values at one location.
Yeah, I agree that there will be cases where there is a natural way to select the site based on what you're interested in. But if that's not the case, I wonder, is there a way to kind of interrogate out the effect of the condition?
Yes, and some people have tried to do that, right? I think, yes, I think that is definitely possible, right? Clearly that's possible, right? But however, I think you may at that point be better going to other approaches, right? Again, max stable processes have their own deficiencies, right? You're making all sorts of block maxima assumptions, or if not, you're having to do stuff with composite likelihoods and stuff. So the inference gets really complicated, right? Whereas I think this is, in terms of an inference, right, is a lot simpler. You have to fit the marginal model, okay, which is so to get onto this kind of standard, copular dependence type scale. But once you've got onto that scale, right, things tend to look relatively easy. And what's nice is that certainly the MCMC inference works very well, right? So the models are relatively stable then, right?
I totally agree with you. I'm an advocate for models that are simpler and more flexible than max stable processes, although they're very elegant. They have a bunch of issues computational wise, or sometimes they're not really realistic in the ways they describe the dependency structure.
Exactly.
So I completely agree with you. Now, my third last question, completely unrelated, it has to do with the marginal modeling. You mentioned that you don't propagate the uncertainty from the marginal model, and I wonder if just, for example, a bootstrap will do the job.
Yeah, we could do that, and to be honest, in other, not in this work, but in other work, we've done exactly that, right? So, or what we do is we take, okay, the correct way of doing this, right, is to set up a model which does which jointly estimates all of the marginal stuff and the dependent stuff in one fell swoop, right? Clearly, right? Okay. So we're trying to avoid doing that because the number of parameters that would be involved in that gets extremely large, right? So what we're trying to do is to do the marginal model first, and then either just pass through, let's say, a best marginal model or a best estimate marginal model to do the dependence modeling, right? Or alternatively, to pass through some sort of ensemble of marginal models which represent the uncertainty in that marginal fit, and then do the dependence modeling for that whole ensemble of marginal models, right? So we have done that, and we've done that with by bootstrap, as you say, marginal bootstrap would work. The other thing you could do is to fit the marginal models, again, using Bayesian inference, and take samples from the posterior of the parameters and use that to do the marginal transformation. It's not elegant because it's one way, right? We're not propagating uncertainty then back from the dependence model back into the margins, which we should do if we're doing the full joint inference. So the correct way is to do the joint inference, but that's hard, right?
I'm going to have to be ruthless there, Phil, and just to not take time away from
absolutely.
Pete.
Sorry.
Thank you.
I promised Pete we'd do this, so sorry if we were just a minute over, but straight over to Pete, who is a statistician at UKCEH.
Great, thanks, Adam. Hopefully you can all see that okay. So I'm going to be talking about sort of modeling some vegetation data, some different plant data, and this is work that myself and my colleague Susan Jarvis have been doing for quite some time in various forms under this sort of large project we have called UKscape, which is stands for Status, Change and Projections of the Environment. So Susan's a quantitative ecologist, and one of the great things about working at UKCEH is that I, as a statistician, get to work with a lot of ecologists and environmental scientists who are excellent at statistics, and often in certain areas know far more than I do, which is embarrassing for me, but great for them. But it's great to work in that sort of interdisciplinary environment. Okay, yeah. So I'm going to talk about vegetation, but generally, this is about sort of ecological status and change. And we know that there's a need to protect and restore healthy ecosystems. There's lots of reasons to do this for the benefits they give both to us as humans that we're only just now sort of quantifying and recognizing, actually, with the sort of the ideas around natural capital, but also obviously the benefits that they give to other species and species give to other species, and that whole interaction within the ecosystem. But to do this sort of requires, to protect and restore these ecosystems requires this understanding of status and change, impacts of certain drivers, to help with potential mitigation strategies that might be needed to protect these ecosystems. So ultimately what we want to do is we want to understand sort of what is changing, to what extent it is changing, and where it's changing. So that's the information that really is needed from a policy perspective to help in doing something about the areas that need something done about them, essentially, to cut a long story short. But what we've actually got really is we've kind of got one thing or the other. In reality, we sort of have a lot of analyses that report on temporal trends of species or of different ecosystem properties. I'm focusing on species today. This is actually the farmland birds indicator that JNCC produced. This is one of the most catastrophic changes and declines that is largely reported. Obviously, that completely sort of ignores space. That's just a temporal trends. There's no sense of are some areas experiencing this loss more than others. We don't know that from these sorts of analyses. Or conversely, there are lots of sort of species distribution models done where we fit spatial models to species data. We understand the relationships, we try to understand those relationships spatially, and then sometimes one may extrapolate with using a sort of space for time sort of substitution approach. Underpinning all of this, though, is the need for good data, essentially. And for trends in particular, there's a need for sort of good, consistent data. So with vegetation, this is something that we've not really had with plant species data over a long period of time. So previously, the JNCC indicators for plant species look like this. So this is in the same report as that farmland bird indicator. And you see that here we've not got a sort of trend, we've just got sort of 3 time periods and some estimates of sort of relative change across those 3 time periods. This was based on data from one particular scheme that I'll talk about more in a moment. That was the sort of the past. What JNCC produced now and show in their reports is this, which is trends from 2015 to sort of present day. Or 2019, and this is based on some different data. This is based on a different scheme. Now, obviously, the data that underpins what's on the left-hand side is still there. It's not gone away, but it's no longer included in the trends on the right-hand side. So you've got this disconnect because it's inconsistent. There's completely different schemes, different data sources, and so there's not been any attempt to sort of rectify the two, if you like. So this is, so I mentioned, this is about spatial temporal modeling. And so the case for space-time here is really to understand, are these trends that we're showing, are they representative? So does the modeling of those trends account for space explicitly? So it's not just driven by data that is sort of from one particular part of the country. As you see on the map on the right-hand side, a lot of data sources are not sort of spatially even in their design, and there's reasons for this, which I'll come on to in a moment. The other case for space-time is, do these sort of analyses help establish targeted management practices that we've seen? Not necessarily. And are these space for time substitutions robust? Can you take a spatial relationship and project that across time? And often we find that that's not actually a sensible thing to do, even though it is commonly done in practice in lieu of any other data. So talking about data, for vegetation data, there's 2 main structured monitoring schemes in the UK that have taken place over the last sort of 20, 30 years. On the left map there, the top right, there's the Countryside Survey Scheme, and on the right is the National Plant Monitoring Scheme. So the reason for this sort of figure, and the plot in the left is sort of when the surveys have taken place over time. Apologies, it's a really poor plot on the left. I did it in a rush, which is why it's so terrible. But they've got very different spatial and temporal coverage, these two schemes. So there's the National Plant Monitoring Scheme doesn't have sort of even coverage. It's sort of mainly dominated around the sort of the south and the sort of Midland type area. The Countryside Survey Scheme is sort of spatially even and representative. It was designed in that way. However, when you look temporally, the Countryside Survey Scheme was done back in 1990. In 2007, started doing some more recently, but it's sort of intermittently done over time because it's a big effort to do it. Whereas the National Plant Monitoring Scheme is actually a citizen science survey, which is why there's this sort of unevenness in the design. And that's been done quite often since 2015, hence that plots that I showed you initially. There's other data as well, which is sort of more opportunistic data. So there's no underpinning design here. This is that the public can submit records if they see something. So if I see an interesting plant or a non-interesting plant, I can submit that record via, there's various ways of doing this. You can submit that record and that will be captured. So that's more opportunistic citizen science recording. So that's just the summary of those two different schemes that I put in. And maybe now is a good time just to mention COVID, like Marian has also done, and the issues that that has brought with these surveys. That's been particularly problematic here, where you've got a design survey that we weren't able to go to a lot of our locations because our surveyors weren't allowed to stay overnight places, which caused a problem. So we did lots of surveying where we could, which meant that our random survey is now biased towards where our surveyors live, which is going to be problematic in the future. And the citizen science scheme, actually citizen science initiative sort of boomed last year in 2020 while people were sort of at home. But what that's done is actually the uptake and submissions boomed, but people weren't traveling. So now we've got, it's even more biased towards where people live, the data there. So lots of different data challenges here with these two schemes, lots of differences between the two, which I won't go into for the sake of time. But you know, the different schemes can record the actual plant data in different ways, whether it's just a sort of presence absence or it's how many was there. And there's different protocols that might be different. One big issue actually is that they sometimes use completely different species nomenclature. So it's very difficult to match these two things up. But what we actually want to do then, and hopefully I've provided the motivation behind this, is to actually combine these data together so that we've got the sort of best of both worlds, really. We've got that spatial coverage, we've got that representative spatial coverage from the random sample survey, but we've got that temporal coverage from the sort of citizen science. And we're thinking not just about what data we have now, but what data we might have in 10 years' time. So that's really the driver why we want to do this, to bring these two data sources together to get the best of both worlds. Two different ways of doing that is either sort of merge the data, something, well, this is how we've thought about it, is you sort of assume that the two different data sets have the same observation process, you sort of pool them essentially and just analyze them in a fairly straightforward manner. Or there's the sort of the model-based data integration, as we've called it, where you explicitly account for the fact that each data source might have a different observation process associated with it, and you account for that in your modeling setup. I'll skip that. And just as an aside, you have to also think, it's not too much of an issue with this data, but when you're doing this, you have to think very clearly about the potential sort of change of support issue that might be happening, and to think clearly about what it is in the model that you expect to be similar and consistent between your data sets and what not, and why not. And often a change of support can be a big sort of a driver of that. So first I'm going to just briefly talk about the spatial analysis that we've done here, which is really about producing a species distribution model. In this case, it was for ash trees. This was motivated some years ago by the ash dieback issue, but we've sort of followed it up now. And you'll see on the left here, we've got presence absence data from our random survey. And on the right, we've got the sort of opportunistic data, citizen science data, that's just sort of observations of where that's been seen. So that's sort of presence only data. So our model, and I'm not going to go into too much detail here, but essentially we've got sort of two components modeled here. So we've got the top sort of 2 bits. Hopefully you can see my mouse. The top bit is a model for our presence absence data, which is sort of Bernoulli distribution, which is a function on the linear predictor of some covariates, a sort of latent spatial field here, and some error. And for our presence only data, that's a sort of point process type model, where again we have some covariates and a random spatial field and another random spatial field. So what we've got here is we've got this bit, this mu, this is the bit we're really interested in. This is the spatial field which will determine the species distribution. That's the bit we're sort of interested in, and that's the bit that's common between these two models here. So that's the bit we're sort of interested in, that's the bit we want to estimate. With our second process, we have this other spatial field, which is accounting for the fact that there's spatial bias in that opportunistic data because there's more observation from certain areas than there are others due to many factors that we don't entirely know. So that's what that second spatial field is doing there, is accounting for that. And the covariates account for the other differences between the two schemes. And then this mu sort of term here is our latent spatial field that we ultimately want to estimate using both data. That's why it's common across both these models. So this, and I have circles to point that out. So this, we fit this using inlay, using the SBDE approach in inlay, which is fantastic because it means these sort of models can be fit fairly a lot more easily than previously in MCMC. We can produce our species distribution map, the uncertainty associated with it, and we can even pull out that additional random field that's accounting for that bias as well, which has a lot of interest in it as well for the people who run the schemes as well. I'll briefly skip over this in the interest of time, but essentially, when you're sort of integrating data in this way, you do need to be careful about bias and whether that might be, if that bias is correlated with covariate effects, what impact that may have. And there's a reference here to a paper that myself and a few others wrote on this issue, that it's not always the best thing to integrate data together. It can just introduce a lot more noise into your analysis. So we thought about extending this to a spatial-temporal model, and that's easy to write. So in this case, we're not modeling one particular species now, but an indicator of vegetation that's called Ellenberg N, which is a sort of composite sort of metric, if you like. And so we can define a spatial-temporal model quite easily in equations. It's easy done. You just put a time subscript against everything, and now our latent spatial process is a latent spatio-temporal process. So that's it's nice and easy to write. In practice, it's much more challenging to do that. So what we actually did initially was just to consider sort of two different time periods. A sort of one 1990, the sort of where our earliest data, and then one sort of more recent. Then we could look at the difference between the two. So essentially, what we ended up doing here is assuming that these two time periods were sort of independent, or the spatial temporal process was independent across the two time periods. And yeah, I'm just conscious of time, so I'll sort of flick through this initially, but you can think of this as essentially within one model, we've done what you could do in two completely separate independent models. You could have fit two completely separate spatial models, spatial only models to the two different time periods, and then looked at the difference. We've done that all within one model, one for consistency, and then two because it's easier to estimate uncertainty around the change. That's what we've done. So we've got these two maps of our indicator from 1990 and from the most recent sort of period, if you like, and we can look at the change now. So we can look at the change between these two, and that is what the policy people want for targeted interventions, because they can understand where things are changing more. We have also started recently to look at a sort of continuous sort of time model, or considering a dependent structure across time. And again, in theory, this is quite straightforward to do. It relies on good data. And although we've been able to fit this approach, assuming a sort of first order autoregressive process, given the data we have over time, we're a bit dubious by the results. So we're actually pausing that slightly now and undertaking a sort of simulation study associated with this to understand the effects of doing this, and again, when that might be advantageous and when not. The advantage of doing this would be that we can then start to think about predictions as well, and predicting sort of one time step ahead. The advantage of doing that, just to sort of nearly finished, the advantage of doing that in predicting one step ahead is that the uncertainty around that prediction tells you something quite clear and incredibly useful and incredibly powerful. So I think, because I'm a keen sort of advocate of adaptive sampling and more targeted sampling with our monitoring schemes, so that we're collecting data that has the most sort of rich information content. One way of doing this is to use that uncertainty in the step ahead predictive prediction to determine where more information would be more useful, i.e., where should we be collecting data from next year. That then feeds back into your model, and the process sort of iterates, and it becomes this sort of dynamic approach. So this, what's on the screen, is kind of like a schematic of that whole idea that we've got two or multiple data sources into some sort of integrated model with covariates. We use that model to produce our sort of map, our data products, and we use the uncertainty or the information around that to then target our sampling and direct our sampling in a more efficient and effective manner. So just to summarize, spatial-temporal modeling is complex and relies on good data. And I think we all know that and appreciate that. But for that reason, especially with vegetation data, which is a bit of a Cinderella of ecological data collection, there's either a sort of temporal or a spatial analytical focus, but that's not necessarily what is required from policy makers for instigating change or mitigation strategies. Data integration can have many benefits, but you do need to be careful and consider whether it's appropriate to integrate or not, and the potential limitations and pitfalls associated with that. And finally, I always sort of like to end on this, is that I do believe that there's an increasing need for more collaborative approaches across disciplines. It's great from my perspective to work with ecologists and environmental scientists together. It'd be great for more statisticians, academic statisticians, to get involved with these sorts of issues as well. And I will finish on that with thanks to many colleagues as well.
Thank you so much, Pete. I see Marian's already started the applause, so I encourage others to do so. And thank you very much for that talk. And you've left a few minutes for questions. So if anyone's got one, please do either use the raise hand feature, or if you don't have that available on your device, then use the chat or just come off microphone. I can't think of any other ways. While those are coming through, I did have a couple. One was on uncertainty, but thought, what was the other one I had? Mine's gone blank just at the wrong moment. On the uncertainty, I was going to ask if you also get joint uncertainty between like the periods. You said you model them together, and is that meaningful to look at how your return parameters are jointly correlated or something like that?
Yeah, it can be. I mean, that is the challenge, actually, is that you can fit is making sure you're fitting an appropriate model, but an understandable and interpretable model as well. And I think that's something we're sort of very conscious of I'm very conscious of in the work, that getting that balance right is important. So yeah, in that case, it is informative and does tell you something different. I can't remember what my colleagues said, but it's this issue of there being different types of uncertainty, and some that you can do something about, because that's perhaps more to do with the volume of data, and others to do so. So in that context, it might be more about that, really, because they're just regions that you're not capturing. So it's not really the uncertainty around the change, which is different to the sort of residual uncertainty that exists, that might be more to do with measurement error or lack of data, etc.
Cool. Have you got time for one question from Marian, Pete?
Yeah, sure.
Yeah. Oh, Marian.
Thanks, Pete. That was really interesting. I wondered just very quickly, you mentioned you were using SPD approach. Was it very computationally efficient? Because we fit some similar types of models to similar types of data, not using inlet, and it can be very computationally challenging.
Yeah, I think the short answer is that it in my experience of using it has huge advantages in computational effort. It can fit very complex models very quickly. There are, and as we found with this sort of the spatial-temporal model, the autoaggressive, I mean, that is slow. There's no magic wand that it's going to fit that in 2 minutes. So that is still slow, but it's hugely advantageous, and it does. I mean, I think one of the things I've noticed with Inler is, I mean, it very rarely sort of breaks or doesn't fit. You've got to be careful, and that's what I was trying to say at the end, that you can specify a model, and it will fit it, and without error, even though it's not done what you think it's done. I don't know if that makes sense, but it's almost too good sometimes that you've just got to be careful that it has done what you think it's done. But I would, I think it's been sort of transformative really, because it's quick. And the other thing I would say about it, it's been a lot easier for my sort of ecological colleagues to get to grips with compared to complex MCMC approaches. So I think that's another big advantage that can't be underplayed really.
Yeah, no, that's great. Thank you.
Sorry, I'm muted. Thank you, Marian. Thank you so much. Thank you, Pete. And thank you, Phil. Thank you to all our speakers. Thank you to all of you for coming. I think we're up to about 25 participants at one stage. So that was actually a good turnout in the end. So thank you all for coming and supporting our environmental section. And there's more talks in the conference. So just a final thanks to our speakers and to Melanie for being in the background, organising us and getting us all connected. So thank you to everyone, and take a break if you need one. And there's more online stuff coming up over the next 3 days. And for anyone in Manchester, I'll see you tomorrow. I'm going in person tomorrow. So yeah, thank you all again.
Thank you.
Thank you, Adam. Thank you, Adam.
Thanks, Adam.
Yep. Bye.
Take care,
Bye,
everyone.
everyone.
Bye, everyone.